Hi, I'm Michael Tsirkin. Welcome to my talk. I work at Red Hat, distinguished engineer, and I'm a chair of the Virtio TC. And today I'm going to talk about hardware implementations of Virtio. I'm going to describe some interesting challenges, some best practices, and answer some frequently asked questions. And hopefully it's going to be an interesting study about building hardware interfaces, software interfaces, and what happens when you try to bring hardware and software under a single umbrella. Just a bit of history. I think 2012 was the first year when we had a hardware implementation of Virtio, which was originally designed for software, for hypervisors, and we started using that for kernel user space interactions, user space to user space interactions. And Rusty Russell was one of the authors of Virtio, thought it's really a random event, but very cool. And then 2017, Intel started talking about Virtio accelerators and hardware, and now we have lots of people doing that. So one of the reasons people are doing that is really network effects. You have tons of software already supporting Virtio. You have Windows drivers, Linux drivers, SPDK, DPDK, all kind of firmware drivers for all kind of devices like SCSI, networking, serial. And so if you build a device using Virtio, you get to leverage some of this infrastructure. You don't have to write it from scratch. That's definitely part of the answer. And how much you can reuse would kind of depend on what kind of device you are building. But there's just so much out there that there's a good chance you can leverage it, a nice chunk of software, and don't have to rewrite it. And a large part of this has been there for years, since 2000 really, since Virtio was originally introduced. And so it's also widely deployed, so you have a huge use base. That's good. So standards are good generally, but I think it's not just that. So there are more reasons and more situations where you gain by using Virtio in hardware. So userspace drivers is one example, and people write it like in Rust, compile it statically, or just link with the library, and you deploy and it works, but then it becomes a challenge to upgrade your application. Any kind of new hardware, you really need to update at least the library and likely also the application itself. And also, kernel really has no visibility into the state of this device. So normal things that you can usually do with user space, like snapshot and restore, also don't work because there's no way to save the state to enable and then restore it later. And if you have a standard interface, that solves it. You can have like a generic driver that can save and restore state, and you can switch between two different hardware cards. Both of them are using standard Virtio, and the application uses Virtio, right? So you get upgrades without any need to update your software. Virtual machine guests, it's kind of the same, really. So people are using pass-through for performance. So guests get access to the hardware directly. But if you do hardware right now, you really cannot move your VMs or guests between VMs running on two different hosts, unless you take great pains to make them look exactly the same. And that's really challenging. So if you have a standard interface, you can standardize on that, and hopefully then you can move your VMs between hosts. And I'm going to talk about this a little bit more. And also, again, we have a standard interface, so hypervisor can figure out what's going on with this hardware, and then it can inspect it for debugging, it can inspect it for migration. So usually, if you are doing things like pass-through, direct access to hardware, then that breaks lots of things we like to do with software, like overcommit and swap and whatever. And it's great that if you have a standard interface, you can kind of switch between software and hardware implementations. So you cannot exactly have the both of both worlds, but you can at least dynamically adjust, and you don't have to have downtime for that. So you can switch between, for example, a hardware implementation of Virtio and a software implementation of Virtio. That's the thinking goes. Well, bugs happen. And if you have a spec, and we are taking pains and working on it a lot to try and make it as specific as we can, then we can figure out who's to blame. Unlike, like I've been in the shoes of a driver developer, and hardware guys always shift the blame to software guys, and we software guys shift the blame to the hardware guys. So at least here you can figure out, all right, one of the guys is violating the spec. There are also, it's also a debugging aid. So you can swap on a different hardware device that adheres to the same interface. You can possibly swap in a software implementation. And then you say, all right, I changed cards, and it starts working. It's a big hint that the problem is in the card. So that's nice. And we are also like generally trying to fix it in the right place. Because any deviation from spec, we can see, all right, the bug is in the hypervisor, let's just fix it in the hypervisor. So we don't proliferate hacks the way people kind of used to do with ad hoc and non-specified interfaces. Then there are some nice properties of Virtio, I think, that actually make it attractive as a hardware-software interface. Some of this is our strong focus on forward compatibility and backward compatibility. I'm going to talk about this a little bit, but generally it's attractive, right? Because upgrading hardware is hard. Then there is use of PCI for discovery. That's nice because lots of people use PCI in the hardware. Our notification mechanism is optimized and happens to be efficient for hardware as well. And then it's also good that we have a good specification process in place. So I'm going to drill down into all of these things. This is how Virtio tries to achieve compatibility generally through feature beats. So there are two of these. There's driver features. There's device features. You end these guys, and both device and driver get the result. And this means that we put out a new spec revision, and that adds a bunch of features. There's no like version that you increment and you have to implement lots of stuff. You can cherry pick specific features. So that makes for a great compatibility story. Now let me talk about the discovery a little bit. So this is just LSPCI. I run it within a VM, and it shows a bunch of PCI devices, and among them you can see the Virtio device. So Red Hat donated specific vendor ID, device ID, bunch of these pairs to the Virtio specification, and then you build hardware that exposes this pair of IDs, and then existing drivers bind to it. So that's great. Well, what else? Driver binds, what happens next? It has to also work. So all of the communication is also PCI-based. So this is, again, this is a dump of the PCI configuration space of a Virtio device, and I highlighted some interesting points. And one is you see the bus master. This means that device is accessing the memory. And so most of the state is managed by driver just by allocating memory from the kernel and giving device access to it. And this is exactly how hardware devices tend to work. This is called DMA, direct memory access. Then the other part is the second square. You can see some device memory. So driver can initialize the device through this device memory. Again, this is very similar to the PCI. I'm going to talk about this a little bit later. Right? And finally, we have message signal interrupts. This means we have signaling from the device to the driver. Let me just talk a little bit about device memory. This is going to be important. So we have actually two kinds of configuration spaces. We have the standard PCI configuration, and we have Virtio specific configuration space. in device memory. This is used to set up the device. That's one part of device memory. And another part of Virtio device memory is notifications. This is used for operation. They are kind of kept separate. And this is, as you will see, this actually is one of the things that enables all kind of optimization tricks. So we have the memory on the device, but most of the state is not there. Most of the state is in the RAM. It's just accessed by device in structures that we call the Virtqueues. And this queue just have a bunch of descriptors, and each has some flags to tell the device that what it can use a descriptor for. And it has an address and a length, and that's like bog standard. You look at random hardware device, you typically has something like this somewhere in memory. So it's good. It's easy for hardware to implement Virtio because they're just used to doing this thing. Now, generally, hardware accelerators kind of tend to use less CPU than software, right? But sometimes there are things where software is faster. So one of them is when you have to synchronize, because software benefits from cache synchronization that most CPUs have, and 7P systems have, right? And if we are talking about a device across PCI, that's not uniformly available. So when you are talking to a device, you have to use some special operations to synchronize your memory and make any changes to in-memory data structures appear in a correct order to the device. So like you are storing a descriptor in memory, and you may want to make sure that all of it is in there in memory, but only visible to the device after the data that the descriptor describes is visible to the device. So in this kind of situation, the software implementation actually can be a bit faster. So we have a special flag, and you have a hardware implementation. You have to say, all right, you have to disable all of the optimizations that rely on cache coherency. That's the other platform flag, feature flag. And then there are platforms where you have to work even harder. So you have to actually copy all of your data into a specific bunch of addresses which are accessible to device, or flush some kind of cache, or set up some mappings in the IMMU. Otherwise, the data is not visible to the device. And again, that kind of slows the hardware a little bit more. And we don't want to pay this penalty for software devices. So again, we have a feature flag that hardware implementations set. And then the driver knows that it needs to work a bit harder. So this is just best practices. You're implementing a Virtio device, what you should do. You should definitely implement at least 1.0. That's the version 1 flag, means 1.0 and up. You should set the other platform and the access platform flags. At this point, I'm thinking, if you're investing engineering efforts and you worry about things like, well, what about OpenBSD? They didn't update the driver to 1.0 yet. Just put the engineering there. Sorry? They have now. Great. Sorry. I was wrong to pick on the OpenBSD. On some operating system. Right. There are a bunch of reasons not to support legacy interface, but in particular, you cannot expose all these nice flags. So you don't know that you are not running on one of these Virt platforms. Maybe someone plugged your card in one of these, where you need to work harder for the hardware to work. On a bunch of platforms, the legacy interface used I/O instead of memory for device access and notifications, and that's slower generally. On x86, it causes exits on KVM typically. So you do all this. What do you then? How do you use it? Well, first of all, you can just use pass-through. bind the VFIO driver to your device, right? Pass the device on to the guest. And assuming that your card has a bunch of virtual functions, and each virtual function implements the Virtio spec correctly, right? Then, for example, within a VM, you can just load the Virtio driver, and it all works, right? No vendor-specific tricks, nothing. At least it works. And I think some people did, and it works for them. So that's great. So one of the names for this, is full offloading, because you actually put both the configuration parts and the data path operation all in hardware. So another option is to keep some part of the functionality in software. So we want to somehow inject a vhost mdev, that's a red square here, between your guest or your software and the device. I'm going to talk about this a bit more later. But the idea is we just intercept the control path operation. And that's why people call this data path offloading. And this mdev driver can be hardware-specific, vendor-specific. It can access the VF, but it can also poke at the PF if it needs to. And it will intercept the control path operation. It will implement the Virtio spec, just the set of parts in software. And the data path, we want to do it in hardware, kind of like this. So in this example, we have the configuration memory. The PTE that backs it in host page tables is marked not valid. So attempts to access that trap to the hypervisor, and then you can forward it to this mdev driver. And the notification memory is backed by a valid PTE, and then it just can go on to the hardware without any traps, just like pass-through, right? And then we have the guest RAM. As I said, most of the structures are there, and they just need to be mapped in the MMU, made accessible to the device. And then, again, it's exactly like pass-through. You get the same performance. Oops. Sorry. What's going on? I lost my place. This one. Yeah, just wanted to point out something here. So what made it easy is the fact that most of the configuration is in device memory and in an area separate from the notification. And notification is kind of controlled and very, very narrow interface. Unfortunately, it depends. And there are some devices which have like a control Virtqueue. And then they need to do some configuration through the Virtqueue as well. This is harder to intercept. Well, it's possible. Like, I think the Virtio file system, for example, it tends to do its own version discovery and configuration, but that only happens at boot. So maybe you can start with a software implementation, and then after everything is set up, you switch over to the hardware. But this is something we should keep in mind as we are building new software. We should try to do all of the discovery should happen through memory if we can. That's easier to intercept if we are considering supporting hardware implementations down the road. Well, once you have this vendor-specific mdev device, in the middle, you can do a bunch of tricks. One interesting possibility is to do partitioning. So you could have a single VF, and you have a bunch of virtual queues, and you give some of the virtual queues to one VM, and you give another set to a different VM. And you can map notifications correctly, and you have two mdev devices emulating the Virtio specification, just the configuration part in software. If you do this, you need to isolate the Virtqueues from each other. For example, maybe you can do this using the process address space identifier extension in the PCI Express specification. So once we have hardware that supports this passive extension, we can attach different process identifiers to different Virtqueues and then have them isolated to different VMs. Unfortunately, it's not yet widespread, but hopefully will be. So another use for mdev is for migration. So if you're gonna move a guest between VMs running on two hosts, they have to appear exactly the same to the guest. And one way to do this would be to have the mdev be controlled from QEMU, for example, and then you force it to a subset of features that can work on both the source and the destination. So QEMU kind of blocks specific features on the source which are not available on the destination, and vice versa. And then once we have this compatibility in the configuration, we can safely move the guest, and it will not notice that anything happened here, right? Again, mdev allows some visibility into the state of the device. So we don't have full introspection in the Virtio spec, so you need some kind of vendor-specific capability in order to be able to load the state of your device. So you would get it through the mdev driver, send it to the QEMU, and then you can send it over to the destination, and there hopefully load it back into the destination device. I hope we'll extend Virtio spec down the road to support this introspection, but that's where it is now. Device bugs, also fondly known as quirks. So hopefully you can fix the hardware. How do I fix the hardware? Well, a lot of functionality is gated by feature bits. So if you just have just the feature bits, maybe in some programmable memory, then you can disable parts of hardware, hide them from software. So you find a bug in a specific feature, you can mask that. Even the whole configuration is not too big. With feature bits, right now we are kind of a bit more than halfway through the first 64 bits, so I would suggest like new devices, just do like 128 bits. That shouldn't be too expensive. Hopefully it's fixable. Again, it's always possible to say, we cannot fix this device, let's just use the vendor-specific driver. It's not the end of the road, doesn't mean that you will have to write the whole driver. You might use some, well, you know, you can copy some parts of your Virtio driver, you can maybe link it to the library. But sometimes you might be able to even avoid changing the hardware completely. So again, if you have the mdev driver, right, that can poke at the VF or the PF, figure out that the quirk is needed, right? And then it can mask some of the features because the feature bits are in configuration space. So they're kind of easy to intercept. And you might need to actually set some feature bits that are missing. I think it actually, I had a talk to a hardware vendor, and they didn't set the platform access flags, and then it didn't work with the IMMU. So you can work around this in the mdev. You can set the flag, and then it will be visible to the guest of the VM as if the flag has been set. Well, it's an interesting question how to detect the device. Normally, you'd use just vendor and device ID. You cannot because you want to support the generic driver. Well, maybe you can use a subsystem vendor device ID. You can do this unless you want to support legacy. Maybe that's another reason not to do legacy. But if you do want to do legacy, then we have a proposal on list to like add a special capability that allows you to show, right, yes, I have legacy, but so ignore the subsystem ID, but this is my actual ID. So we are looking at to make it easier. Hey, here's another cute use for the mdev device, write logging. So you need to know which pages change if you want to do a snapshot, for example, right? Because you don't want to dump all of your memory each time. So one thing you can do, you can have this mdev driver allocate a buffer in some format, that hardware knows about, and then give it to the PF and tell it whenever one of your VFs is going to modify memory, I want you to record this in this buffer. And then you can figure out, all right, this is a list of pages that changed since I previously did a snapshot, so I want to do this. Also works for pre-copy migration. Doesn't work for the post-copy though. If I have the time, I'm going to talk about post-copy. But first, let's just bit of administration. So we kind of seem to be to have stabilized the spec at this point, not too much. It's going on, at least with existing devices. Always proposal for new devices are outstanding. So I think we should be able to finally freeze the spec kind of by end of November. And then we start the public review draft. And then it all depends. If people don't find any defects, how long? 5 minutes, all right. Then we'll finalize it. And if not, we'll do another round of reviews. All right, let's do, this is important to me. So you need help implementing the spec. What you should do. First, what you shouldn't do is mail me privately. But do mail the mailing list and copy me, that's great. And you want to make a change to the spec because your device has this great new feature. And something not to do is to lock yourself up and work on the spec proposal for a year and then publish it. Something to do is to start publishing as early as possible. All right, let's try to skip this one. This is just the minimum you need to do if you want to make a change for the spec. Just make sure you don't conflict with others. So for a new device, allocate a new ID and register it with the TC so others don't implement a different device with the same ID. If you're extending the spec, ask for a feature bit to be reserved. We are not short on feature bits. We'll give you a feature bit with just a vague description of what it is. And then there won't be a conflict. And there's IPR compatibility. There's a lot of lawyers speak, but one thing that's definitely important for us is that people declare, all right, I want to put this in the spec, and if someone implements it, I'm not going to sue them. So that's that. I want to talk about post-copy. So let's do this. So page faults are kind of important, and they kind of tend not to work for hardware. But they're nice if you can have them, because you can do overcommit with KSM and swap. And you can do pre-copy migration with write faults, and you can do post-copy with read and write faults, snapshots and stuff. So there is support for page request interface, even if you have hardware that supports that. It all kind of assumes that it can handle the fault completely in the kernel, and that means no user fault FD, so for example, no post-copy. And then hardware support is very limited. Something we could do is if we taught the IMMU drivers to individually protect and unprotect specific memory pages, then we could take a page that we want to move out and protect it at the IMMU level. Then device attempts to access it, it gets a fault. Normally that's an error. Device enters an error state. Instead, we could just pose a specific queue, notify the host through the mdev driver, and then at some later point, you have handled this fault, you have a page, and we can unpause the queue and have it restart and hopefully go on. So that would be nice if someone wants to implement that. This is, okay. So this is another optimization idea. So it turns out that software kind of goes through requests in a queue and just, it has to run them anyway, right? And they all run sequentially on the CPU. But hardware can have lots of resources and run them in parallel. So it's very helpful if we can tell hardware not just there is something in the queue, go and get it. Instead, if we can tell it, all right, and here are 16 requests in the queue, and then hardware can go fetch them in parallel. So that's something we are considering in the spec. Interrupt suppression, people are asking to move it out of RAM because it's hard for the PCI card to fetch it from RAM. So maybe it may be interesting to move it out to the hardware. Interrupt coalescing is kind of irrelevant if you implement it in software because, well, you get interrupt from the actual hardware. Anyway, you're running stuff on the host. So you exit it from the VM. Now you start the timer. Once timer will expire, you'll interrupt the VM again. That's a lot of overhead. But with an actual hardware, then that finally becomes relevant, so maybe we'll add that. So you see, it's very busy space. So join the fun, and let's just leave some time for questions.
I believe you mentioned that you're looking at getting a mdev support, something in the spec for migration. Are you looking at something that will also actually pause the hardware? So get it to a quiescent point and where its state can be grabbed?
Yeah, I'm guessing that that should be part of it.
I have a question regarding the mdev in the pre-copy slide. So
Okay.
you're suggesting that you will use mdev to know what is to do the dirty tracking of the completions of ingress packets, right? So we'll be able to know what were the DMA operations that were done by the hardware, right? But
Yeah.
you will need to intercept the. How do you plan to do that? You are planning to intercept the notification interrupt. But what if the guest is using a PMD like in DPDK?
Oh, sorry. So at least the idea here was that the mdev just programs the PF and tells it, like you still need this capability in the hardware.
Ah, okay. So the hardware is responsible to provide you a dirty log. Okay.
Yeah, mdev just does a setup.
Okay.
And you know, it probably needs to translate things back, so it tells the host, can poke at this buffer, which is in device-specific format, and tells the host, all right, these were the pages that got modified. And again, hopefully we'll standardize at least some of this. I think Paolo wanted.
So usually when you have Virtio features, you disable them, right? You have a set and you can disable all the ones that you don't support. In this case, you have a feature where if it's not supported by the driver will misbehave and will not order the accesses correctly and all that. So how do you handle all drivers running on hardware, and how are they blacklisted?
Yeah, well, there are two things you can do, right? So you can just figure out that you're running specific architecture that happens to be ordered.
Random one.
I know one, but it's popular. And the other thing you can do is just fail gracefully, so you can teach the device that just to fail feature negotiation, so at least it won't, race and just crash on the field, and it will be fail immediately, and someone will say, why doesn't this work on PowerPC? And then they'll read the manual and figure it out.
Hi, while you have the slide on, so there's a lot done in terms of the logging, etc., for pre-copy. Is there anything done for throttling when you're thinking about pre-copy and auto-converge kind of migration?
I don't know. Yeah.
Are we just relying on the QEMU throttling the CPUs would eventually slow the device down enough? Or?
Well, most of the operations tend to kind of be software-driven. Not all of them. So
Probably-
like if you slow down the VM, the device will tend to eventually slow down. I agree it's not universal. Like you have a networking device, you have a bunch of buffers there, and if you just stop your VM, it still might take a while for the device to exhaust all of these buffers. And then it's not great if you exhaust them either.
It's probably
Yeah,
interesting
good point.
to have some protocol extension that will let you to tell the device you're not allowed to write more than X or
Yeah,
some
yeah.
bucket-based thing. I don't know.
Yeah, go ahead and propose that.
Okay.
So on one of the slides, you were mentioning that there were use cases for splitting a virtual function. Could you give examples of cases where this would be useful, and don't you run into cases where you'd have ordering issues between them as well?
Splitting virtual functions. Well, okay. So it depends on the number of VFs that you can have, but it does allow you to kind of do a flexible configuration of you can do the split in a flexible way. So for example, with VFs you have to know ahead of the time how many you want.
But in that case, wouldn't that be, if you were going that way, wouldn't that be easier for the hardware manufacturer to create a single VF where you have to configure the PSIDs?
Sorry, didn't
So
you
why would it make sense in that case to have multiple VFs?
why would you have multiple VFs in this case? Yeah, we probably don't need to. But you know, could be legacy things. I mean,
So-
the PSID has to be supported system-wide.
So basically you're saying if you have PSIDs, then it makes sense to no longer use VFs, but go finer grained using PSIDs
Yeah,
as a, okay.
like if all your systems do support this extension, you probably don't really need VFs.
Hi, could you expand a bit about the access platform? The order platform I understand. Can you,
Sorry, which one?
the access platform?
The access platform. Let me find that. Right. So there are lots of systems where the CPU is kind of easy. So you can store something in memory and it's visible to another CPU. But if you just put it in memory and have a device access it, it won't see the value that you have stored there. You need to actually flush it out of your cache. That's one case. Another is what I brought here, bounce buffers. So there could be specific addresses. They are accessible to the device, and most of the memory isn't. Encrypted VMs come to mind. You kind of mark specific pages and non-encrypted. These are accessible, but most of the state isn't. And IMMU is another case in point. So you cannot just take a random page and just give it to the device. It will fail. It's intentional for security. So if you want it to actually succeed, you need to enable this temporarily in the IMMU. Then device does the access, then you disable it for security again. So that what the access platform says, it really says, I know when it was part of the hypervisor, you didn't need the security, all of the memories was accessible, you didn't need to work hard. But this won't apply here. You have to work hard. Disable these optimizations, please. Basically, if you don't know, and most independent hardware vendors won't know where is a specific card going to be plugged, you basically just set this.
Okay, last quick question.
What vendors and what's the performance?
What's the performance cost? Performance cost would depend. Yeah. So if it's an embedded system, right, then you might know that your card is actually running on PCI bus that has complete access to all of the memory. There's no need for tricky flushes, and there is no IMMU in this system. Then you don't have to set this flag. If you're building like a NIC based on the Virtio networking specification, then you're a vendor that wants to set this in the feature bits. I'll have to go and look and see whether they gave me the permission to give the names. I don't know. But we have, on the Virtio OTC, we have a bunch of vendors participating, Intel and Huawei and a bunch of guys.
Okay.
Thank you. Thank you. You've been a great audience.